tuning in. This video is going to be the first, potentially, in a series of videos about how I view the natural universe with regards to things like cosmology and quantum interactions and so on. This is not going to be highly technical at first, but I will presume that you have at least a basic understanding of physics. Again, nothing technical or complicated, but just kind of the basics. So today, just as a primer to give you the kind of understanding that I think I have, and please feel free to comment. I want to increase my knowledge, I don't care if I'm wrong. But let's talk about the beginning of the universe. This is a misleading term, and it's disappointing to me how many times we're still thought to think of time as a line, even when we're talking about cosmology and quantum interactions and time and that sort of thing. Most of you are probably familiar with this, and hopefully I'll remember to put the right graphic there. And you can see over to the left here is generally where people think of the beginning of the universe, and then the expansion happens out from it, kind of in a line, and everything we are is over at the right side, moving through time, so to speak, because we are, I guess. And eventually the end is somewhere way out far on the right past us. But this is not a useful way to think about how time works. Because then people will ask questions like, what happened before the beginning of time? And in my mind, this question does not make any sense. However, the great majority of people still think about it this way, and I'm not sure why. For you see, this kind of graphic does not do justice to the idea that time expands in every direction all at once. So when you think of the beginning of time, the beginning is not some finite point in the past, so to speak. The beginning of time is literally, I think, the center of the universe with regard to time. So what that means is, when you're thinking about time, think of it like a sphere, not like a point and then another point. This isn't linear numbers. So when you think of the expansion, imagine that tiny little point right dead center in the sphere. If we pretend for a moment that time is the Earth, the beginning of time would be the center of the core. Now you ask yourself, what's before the beginning of time? Literally nothing. It's the most infinitely dense point there is, you see. So from where you are, and again, if you want to pretend that it's the Earth represents time, then you also need to imagine that the Earth is constantly expanding away from that center, and us up here on the surface, that's the present. As you go further into the atmosphere, that's kind of the future. The past, from our perspective, again, this is all from our perspective. It's not actually absolutely the present, future, and past, but it is from our frame of reference. The further out you go, away from the center, the later in time it is, so to speak. Again, this is not a perfect analogy. In fact, as Feynman might have said, it's cheating very badly. But it gives you a better visualization, I think. So what happens before the center? Nothing, really. Except that time is strange, and so you actually have an infinite number of centers, but that's another time to discuss that. But realistically, if you go backwards from where we are on the surface to the center, and you say what happened before it, well, nothing. You come back out into time. You come back out into the universe somewhere. So before the Big Bang is just another direction toward the future. If you drilled a hole straight through the Earth in this analogy, right through the center, you're going to end up on the other side of the Earth, you see. Now when you get to thinking about time and this sort of thing, we'll eventually get into this. I expect plenty of questions down below. I've got a document I'm working on. Maybe I'll make a book someday if I actually get everything screwed around right here, and this makes as much sense to you guys as it does to me. But the other thing we need to think about is time is like matter or energy, in that I think that time should also have things like anti-time and dark time, just as matter has antimatter and dark matter, and energy the same way. But again, that's beyond the scope of what is the Big Bang. What was the beginning? The beginning was literally that singularity. And it's important to note, and we'll get into this in more detail later, because I don't want this to be a very long video. I just want it to be a primer on a very basic concept, at least in my head. But the beginning is literally where it all starts, because before it doesn't make any sense, because you can't go smaller than the smallest point at the beginning. Now, when you push time down to that tiny little point, the laws of physics stop working, because there's no time for them to work in. All the matter and energy is infinitely compressed at the beginning of time, so there's no time for the interactions to happen. That's part of that expansion. Then, if you're familiar with the basics of the expansion, you know that the strong force kind of happened first, and the weak force, and the electromagnetic, and then the gravitational as you go out through time. And this is because those interactions can't possibly have existed before that, because it takes at least that much time, literally, for those forces to become distinct. So if you want to imagine it, this is, again, the way I think of it, and this is going to be very simplified, but the way I imagine it is, the strong force has, let's say, the lowest density in time. And again, I could have this backwards because I'm not a mathematician. I'm not even really a scientist in this regard. This is just how I think about it. And you say gravity has the highest density in time. What this means is that time affects it the most because it takes the most time to do it. This is one reason that the center of a star is older than the outside of a star. Because when you talk about the effect of time, you're talking about how the density of time changes, or rather, the density of the forces within time. And again, we'll get to all this later, I'm just throwing it out there. So another way to think about black holes, for example, is not that they're infinitely dense, although they are mathematically from our perspective, but they're actually moving another direction in time, and that's why Hawking radiation seems to go the other direction in time. Now, if you're not familiar, light waves and other forms of radiation also do the same thing, as is famous with the double slit experiment and so on. Photons go every direction in time all at once, and when you view them, you're not collapsing the thing itself so much, but you're seeing where it was from your perspective at that time, so to speak. But again, we're not going to go into much detail on that right now. I just wanted to get the basics out about the beginning of time, and all of this is related to it. And I even have a hypothesis on how the subatomic particles work with relation to this sort of wave function and sort of thing, but let's not go there right now. Right now, let's again talk about time, the expansion, and why there was a time with nothing. And if you enjoy this kind of thing, I'll keep doing it. I mean, I'm going to keep doing it anyway, but I need to start somewhere, and this is a complicated thing. Although it's actually pretty simple when you get your head around it, kind of like playing piano or learning to knit. Once you got the basics, it makes a lot more sense, but until you do, it makes none. And again, I am not a particle physicist, I am not a cosmologist, I am not a studier professionally of any quantum mechanics or nothing. I'm just a layman who happens to see things this way, and maybe I'm seeing it in a good way. Maybe I'm not. I want your opinions. I've got some from my other friends already. Again, we're going to make this a fun series, I hope. I hope you're going to enjoy it. I hope you ask me questions. I hope that we can learn something together here. Increase our collective understanding. And again, if I'm completely wrong, or I'm insane, or you think I'm stupid, or you think that something violates the Dirac-Fermi properties of it, or you think that it just can't possibly work that way, that's fine. I want to know that too. But again, this is how I understand it, more so than necessarily how it actually works. As Krauss put it in the book The Quantum Man, sometimes it's psychologically useful to think about the same thing in a different way, in more than one way, to describe it for a different frame of reference so that you can understand it better, even if it's the same thing. And that's all I'm trying to do here. And I thank you for tuning in. Give this a like, a thumbs up, go ahead and vote it up. Subscribe to me if you want to hear more stuff like this. Leave, again, all your comments down below. Leave them long, leave them short, I don't care. This is about discussion. I would ask that you not spam, because I do get a few bots, and I might mistake you for them if you're just trying to put your Instagram down there or something. But beyond that, try to keep it civil. You can call me an idiot and still be civil. And I look forward to making more of these videos. Thank you for your time, and as always, this has been Reverend JR, signing off.